For my part, I'm going to talk about introduction. What is batch liquid reactor? Batch liquid reactor is a generic term for a type of vessels that are widely used in process industries. So what kind of process that we use batch liquid reactors? Well, batch liquid reactors are commonly used in various operation systems such as solid dissolutions, crystallization, batch distillation, and polymerization. A typical batch reactor consists of a tank with an agitator or a heat or cooling system. So what is an agitator? Agitator is an impeller blade that are mounted in the shaft. A wide range of blades are used, and the blade covers about 2/3 of the diameters of the reactors. Where viscous products are handled, anchor-shaped paddlers are used, which has a close clearance between the blade and the vessel walls. The heating and cooling system, let's say, in order to remain the reactant content, you need a desired temperature. So you need heat. So heating or cooling coil or extended jack are used to add for heating and cooling the reactor. The heat transfer fluid passes through the reactor, helps to add or remove heat. Okay. Within the chemical and pharmaceutical industries, extended jack are more preferred because the vessel can be easily cleaned. The extended jack can be defined in 3 parameters. One is response time to modify the jacketed temperature. Next one is the stability of the jacketed temperature. And the lastly is the uniformity of the jacketed temperature. Okay. Now I'll be discussing about the applications of batch reactors. Batch reactors are often used in the process industries. Batch reactors also used in lab, many lab applications, because they can produce a small scale production and inducing fermentation for beverage products. Batch liquid reactors are also helps in experiments such as kinetics, volatiles, and even thermodynamics. Batch reactors are, in industry-wise, batch reactors are commonly used in medicine production. But it's seldom you can see them because they are expensive and also as a variable production reliability. I'll be talking about the main objectives, 3 main objectives in this experiment. Okay, first, to prepare calibration curve for conversion and conductivity. This is to compare the rate of reaction later on. Next is to study the best application reaction of ethyl acetate and sodium hydroxide. And the last one is to study the effect of temperature on batch application reaction of ethyl acetate and sodium hydroxide. This is to see at which temperature the highest rate of reaction. So it's me again. Now I'll be talking about the summarized version of the theory. In batch reactions, there is no feed or exit stream. Therefore, we can summarize the equation into the rate of A loss within the reactor due to chemical reaction equals to the rate accumulated by A within the reactor. The rate of reaction of component A is defined as negative RA equals to 1 over V delta Na over delta T, which is mole of A produced by the reaction divided by the volume times time. By this definition, if A is reaction product, therefore the rate will be positive, and if the rate is reactant which is consumed, the rate will be negative. So rearranging the equation, Ra times V equals to Na naught delta Na over delta T.
We're talking about the literature review about our project. Okay. The reactors are very special, are very important in the industries. It takes your raw materials and undergoes a chemical process and produces your desired products. Now the reactors are the cause of this chemical process. There are many types of reactors. What we came across with was CSTR, it's a continuous stirred tank reactor, PFR, plug flow reactor, PWR, and of course the batch reactor. Specifically, our project was about the batch reactor, the stirred tank batch reactor. That means there was a stirrer in our batch tank. Alright, so let me talk a bit more about the unit that we have come across with. Our unit had a reactor, of course. It was made out of glass wall and 2 silver plates on top. It was vacuum. The reason why it was glass so that we could see the reaction happening in our own eyes. In the glass reactor, in the glass wall, we had a cooling jacket, we had a stirrer, of course, and we had sensors to measure the conductivity and the conversion of the reactants inside. Next, our unit had feed inject system. This feed inject system was 2 10 liters tank, which consisted of sodium hydroxide and ethyl acetate. Now these 2 reactants will go through a pump, which then the pump will pump through the reactants into the reactor. So the pump plays an important role. Moving on, we have a water bath. Our water bath was actually a cooling system where we just injected the hose into a pipe of the sink in the lab. So the pipe will be cooled, the cooling water will be coming in, cooling the reaction from happening, and come out warm water. So that's was our water bath. Next thing is our control panel. Our control panel was very important, so because it controlled the temperature, it turned on and turned off the pumps, and it turned on the temperature so we can control the temperature of the reactants in the tank. Moving on, pause. Was the dynamic actuation system. This consisted of a computer. The computer will take all its readings and whatsoever, because the computer was playing an important role. Basically, it's just a computer consisting of many programs and stuff, so that we can detect the conversion and the conductivity. Alright, so using a preset value for the batch reactor, we can calculate the rate of reaction. Alright, so I have done my part, and I'll pass the mic on to the next person.
Hello everyone again, it's Ali. Now I'm going to do the methodology part. Actually, we did the experiment in 2 parts, which part A and part B. When we go to part A, first of all, we have to make sure that the equipment is under proper condition. Secondly, we have to check if the valves are closed or no, because we have to make sure there is no inlet of any solution inside the tank. After that, we have to make sure that V1 is open, which is ethyl acetate is pumped to go to the first tank. After that, V2 is open, so that sodium hydroxide is pumped until 2 liters with the first one, which is ethyl acetate. Then we have to close V2, no more. Until it's 2 liters, we have to stop. After that, we have to set the temperature to 30.1 degrees Celsius. Then the data will be recorded, which is about the conversion versus the conductivity. That's all about part A. When we finish part A, we have to go directly to part B. What should we do and what should we make sure of in part B? First of all, we have to set the temperature to 35.8 degrees Celsius. Later, the data of conversion and conductivity will be recorded inside the computer. At the end, we have to check and study the effects of different temperature inside this experiment, as we had 2 different temperatures, one is lower and one is higher. So we will see which one has a very high rate of reaction and which one has a very low rate of reaction. That's it about the methodology.
Today I will conduct about the result for the experiment we conducted past few weeks. The experiment is divided into 2 parts. The first part is adjust the temperature to 30.1 degrees Celsius, while the RPM is adjusted to 202.4 RPM. So from the part A, this is the result we get. For the conductivity is decreased by the time increase, while at conversion, the conversion is increased until the certain level when the time is increased. Next. So this is the part B of our experiment. This experiment is adjust their temperature to 35.8 degrees Celsius, while the rotation is adjusted to 204.1 RPM. The temperature is adjusted higher than the previous experiment, and the conductivity, obviously it takes shorter time to achieve until stable, and the conductivity is decreased by the time, and still the same, conversion is increased by the time, but the difference is the conversion got negative value here. It started from negative value here, and it takes shorter time to achieve the steady state. As a comparison to the first experiment, this experiment takes shorter time to achieve steady state level, and by adjust the temperature higher, the result we get is the time taken to get the result steady state. This is the calculation part, and the equation is stated upstairs, which is NaOH plus CH3COO C2H5 equals to CH3COO and Na plus C2H5OH. And this equation can be simplified as A plus B equals to C plus D. And due to this is the elementary reaction, and the rate law can be written as below, which is negative Ra equals to Ka times Ca times Cb. And from the experiment, we know the value of Ca and Cb, and so from the equation we calculated the K value is 0.1885 meter cube per mole per minute. Given that the graph slope is negative 0.1327 and the reaction is 2. Therefore, the standard deviation is 2.146 and standard error is 0.3793.
Again, I'll be talking about the discussion in our project. Okay, as we know that when it's a lower heat being supplied, the rate of reaction is slower. For instance, you make a cup of Milo and your water inside there is very low temperature. You mix your Milo in, you keep stirring, and you get angry because it's not mixing. It's because the temperature of the water is lower, so the rate of reaction of your Milo is going to be very long. So when the water is hot, it will be almost instant when you make your Milo. Same case goes over here. The higher temperature, higher the rate of reaction. For our case, the saponification rate. We discovered the saponification was higher when we used a higher temperature. So, let's move on. The formation of the vortex in the reactor. Now, the formation of the vortex played a role in our rate of reaction. It gave a negative value actually. It made our rate of reaction longer. Now, what is a vortex? You say it's a whirling pool. It's something whirling which it may be fluid or air. Next will be the formation of vortex in the reactor. Now, what is a vortex? A vortex, it's a whirlpool of fluid or air. It creates a spinning motion. Now, this spinning motion will create unreacted region areas in the reactor. So that's why the reaction rate will actually be longer with the formation of the vortex. Now, a vortex will actually push the particles to the walls of the reactor. So the particles which are on the outside will not react. That's the meaning of a vortex. Furthermore, a vortex will make the velocity
the angular velocity of the particles different according to how close are they to the stirrer. This creates the pushing effect of the particles to the glass wall. Next. Okay, it will be the absence of baffles. The absence of baffle actually empowered the formation of a vortex. The baffles the purpose of the baffles were there to actually destroy the motion of the water, the whirling motion of the water. So in other words, destroys the vortex. What is the baffles? The baffles are just two slight things that makes the reactor look smaller on the inside. It's just, it can be 2 or 4, how many, depends on how many you need. So yeah, the absence of baffles de-empowered the vortex. Next. Heat is being added and taken out simultaneously. Now, how is this happening? The heating coil in the tanks heat up the reactants, and the water bath cools down the reactants in the reactor. Now, as we know, when you take out heat from a reaction, the reaction tends to head the other way around, behave backwards. In other words, the rate of reaction is disrupted, so it goes slower actually. Hello, and I'll be talking about the modification. Cedric again. Alright, so as we discussed in the discussion, the absence of the baffles empowered the creation of the vortex. So it is very obvious we should add baffles into the reactor. So it would disrupt the formation of the vortex. These baffles we can add 4. 4 would be the most preferred amount. Towards the industries, they always include 4. Next thing is the type of blade used. Alright, the reactor design was like this. The glass wall, and inside was the cooling jacket. The stirrer was actually in the middle of the cooling jacket. So when the stirrer spins, the outside is spinning much slower, or not even spinning at all. That's what we said in the discussion earlier. The particles are being held at the side of the wall. So there's no reaction taking place on the outside, the unreacted region area. So what we can do is to add a bigger blade. The blade should be placed downwards outside of the cooling coil and be spinning on the outside there. So it could be almost touching the sides of the reactor. In this case, the whole reactor will be spinning, the whole fluid will be spinning almost at the same speed. So the reactors at the side of the wall will be reacted. It would not be stationary there and be an unreacted area. Almost everything will be reacted off the reactor at the same time. So the rate of reaction everywhere is almost constant. It's almost the same. Last thing is, we should measure the inlet and outlet temperatures of the cooling water. Pause. Alright. This step is important so that we can know the right amount of temperature required just to cool to take out the right amount of heat of the exothermic reaction. Now, if our water that we presume was cold, it was a bit cold, it took up too much heat from the exothermic reaction. So this slowed down our rate of reaction. So by doing some calculation, we can find out the right amount of temperature for the water, for the cooling water to go, and the right amount of the velocity for it. So if we have all these things done, we can find the right amount so that the heat taken out will not be excessively taken out, but at the right amount, without disrupting the rate of reaction.
This is me, Ali, again, and now obviously I'll talk about the last part of our project and experiment, which is the conclusion part. First of all, the saponification process. As my friends already told us before, the saponification process of sodium hydroxide and ethyl acetate is held in a batch reactor under very regulated and fixed temperature. It's about 40 degrees Celsius. The conditions and the assumptions there is that the concentration of the reactants will be about constant. In the whole part of the reactor, the bubbles, the pipes, the valves, anywhere inside the reactor. This is our assumption. Okay, now let's go to study the effect of a lower temperature on the reaction rate. In this experiment, as we have seen, so far from the results we have got, that the values will be very different from a lower temperature to a higher temperature. And of course, a lower temperature, the reaction rate will be very low. Why? Because the reaction constant will be very low. Can you see the result? Let's see the result at a very lower temperature. Okay, here we go. At 30.1 degrees Celsius, this is our lower temperature. The conductivity results and values goes from a set point which is about 11.2 or 0.5, and then until it reaches a very steady state to 27 minutes. This is a very large value. Same goes here for conversion. It goes from initial point until 27 minutes, so that all the reactants will convert into products. But when we compare these values to at a very higher temperature, was about 55.8. Let's see the result. This one, for conductivity, it will have about the same behavior, which goes from initial point until. But here's the difference: 23 minutes. That means it's a very shorter time. Same goes for conversion. At 23, the whole reactants will convert into products. That means at a very higher temperature, we will have a very less time, so the reaction rate will be very faster. Immediately, we will convert our reactants into products compared to at a very lower temperature. We will have to wait for a very long time until the reactants converted to the products. I think this is all about the production of our reaction that we have got from NaOH.